It's my privilege to introduce Todd Murphey, who will be giving the RA seminar. Todd, I guess, was born in Flagstaff, Arizona, or at least grew up there, and then went to the University of Arizona, where he got his degree in mathematics in 1997. After that, he went to Caltech, which is where I also went to school, so we're academic brothers, but we don't overlap. So I actually didn't know him that well while he was getting his PhD. He got his PhD in 2002, and I guess the punchline of his PhD is you really don't have to worry about friction that much.
So for all of you that hate modeling friction, talk to me.
After that, he went to the University of Colorado at Boulder, or University of Boulder?
University of Colorado at Boulder.
University of Colorado at Boulder in swanky, fashionable Boulder, Colorado. And he hung out there. Well, actually, he postdoc with Kevin Lynch for a year, and then went to the University of Colorado at Boulder. And then I guess he loved working near Kevin so much that he went back to Northwestern, where he's now an associate professor, doing all sorts of interesting things in mechanics and marionettes and controls. And I'm sure Todd can probably explain it better than I can, so I'll give it to Todd.
Thank you very much. So first of all, I'm thrilled to be here. It's a real treat to be able to come to the Robotics Institute and meet with people and to be able to talk about the stuff that we've been doing. What I'm going to talk about today is largely work from the last 2 or 3 years. And it's work that was motivated by thinking about marionettes. I'll tell you why we were interested in marionettes in a moment. But the sort of punchline in a way is, how do we think in a systematic way about how choreography encodes information about complex systems that might be otherwise intractable to work with. And just to convince you that marionettes are kind of an exciting example of a complex system, this is sort of a picture of what we originally visualized building. This isn't what we're actually going to build, but it has these multi-degree of freedom articulated bodies, so something like 20 to 30 degrees of freedom there. They're all actuated, and they're all connected by these strings. And so what that means is that you have this very high degree of freedom system. Because of the strings, there are mechanical degeneracies, and because of the strings, there's all these closed kinematic chains. And so if I told an aerospace engineer, an aerospace control engineer, I've got this system. It's about 50 degrees of freedom, and it's degenerate, and it's got all sorts of constraints, and I want you to do something useful with it. I probably wouldn't get a terrific reaction, right? Like, this does not feel like a particularly tractable problem. But puppeteers do this all the time, right? Puppeteers get puppets to imitate human motion, and they do it with articulation that's extremely different from the way people are articulated. And so somehow they're solving a very high-dimensional motion planning problem in a very coherent way in order to get puppets to do something that's understandable to the audience. This is actually a collaboration with Magnus Egerstedt at Georgia Tech, with the Atlanta Center for Puppetry Arts, and with Lanny Smoot at Disney R&D in Glendale, California. So just to convince you that I don't solely care about marionettes, related problems include, how do we model a physiological abstraction of the hand? So where the hand is articulated by tendons. And these tendons somehow seem similar to strings. Actually, Francisco Valero Cuevas was the one who, as soon as he saw the marionette simulation, he immediately got really excited because he thinks about hands as basically being marionettes that have to manipulate the world. And they had lots of problems, even just simulating a system like this, particularly simulating it while it's engaged in a grasp, and hadn't even gotten to the point of being able to design a controller that would manipulate an object. This BattleBot is, in its previous life it was a BattleBot, now it's in my lab. It's a skid-steered vehicle, and you could probably model the inertia of the main body of the vehicle. It weighs about 100 pounds, so it's pretty big. And you can model a lot of things about this vehicle quite well, but the thing that might not be so easy to model is its interaction with the ground. Right? The tires have a complex friction-dominated interaction with the ground, and as the terrain changes in a way that you may or may not be able to measure that interaction changes as well. But from a planning perspective, really the two salient modes that this skid-steered vehicle can be in is either in a stick mode, where it's going straight and it can't turn, even with small amounts of differential torque applied to both sides of the vehicle, or it's in a turn mode. And if you're on a really slippery surface, like if it's icy out, if you apply too much differential torque, it's going to turn and go unstable. Whereas if you're on with the same differential torque on something like asphalt, that won't turn at all, right? So being able to estimate, am I successfully breaking that condition in order to be able to steer the vehicle, is actually an online estimation problem that we need to be able to solve. And it's one that is in some sense a choreographic problem, right? Like we want to understand in very high level terms, is the system sticking or is the system slipping? Not in terms of the physics, which is sort of difficult to understand. So this is the vehicle in my lab, and it really is true. Like, so people who use skid-steered vehicles in applications like agriculture often say, well, it always slips all the time. But the problem is that that's because they're on soil. And so on soil, it's actually a reasonably good abstraction that it always slips all the time. But you can actually apply a substantial amount of differential torque to this vehicle, and it'll go straight down the hallway in a perfectly straight line, and you would think that you were steering if you were being naive about how you thought about the estimation process. And so this is a system that you can write down differential equations. So this is the mode where it's sticking, and the key thing is that the orientation of the vehicle doesn't change, and in fact even the velocity of the orientation is 0. So there's one mode where we just move in a straight line, and all these forces are the forces that I can apply to each of the wheels. And then there's another mode where the orientation is allowed to change. Matt?
So I would think that the tires would deform when you apply a differential torque, and it would actually turn gradually as you...
So these are very rigid tires. I mean, I suspect that that's true. If you had a really sticky surface, even with these tires, you would see that deformation start to occur, and you would get a slight turn. But you wouldn't be turning nearly as much as you thought you'd be turning.
And I've tried to get students to work on this. I could never get any, so I'll give it to you. Maybe you have a student who would do. If you did apply some differential torque and then move back and forth, would that be an accurate way to turn? But
I don't know. I could spend the rest of the time pausing, thinking about that problem, but that may not be the best use of time. But I'm not certain. So the key thing here is that in talking about this problem in particular, you can it probably feels feasible that you could write down a model, right? And as soon as you are able to write down a model, then suddenly other things that you might want to do, and I'll discuss what those might be in a moment, become pretty feasible. But a lot of this talk is about what happens when you can't write down an explicit model like this, like write down explicit equations. What do you do in that setting? Okay, but this is what we want to actually have happen. So what we want is to take choreography. So this is an Atlanta Center for Puppetry Arts, and I hope that you can see this. I think once I start moving, you'll be able to see it. This is a play from the Atlanta Center for Puppetry Arts, and this is a Leonardo da Vinci as a medieval superhero. He uses his inventions to battle the niece of the Pope at the time, who's busy oppressing everyone in Italy. And so when they fight, right, they have to interact. So the motion it's not perfectly tracking like what a real person would do, but actually, I mean, the body language is really quite clear, right? So she's taunting him and all these things, and these are all things that we can immediately pick up on and identify. And the goal of this project, right, so you have these they're going off in the distance now, so this is now a small puppet that creates the illusion of distance in the background. And then when they come back into view, there will be a large puppet that's dressed the same way, right? So these are very, very highly articulated, very under-actuated systems that when you look at what they're doing, they're easy to understand. And so the goal of this project, and you'll see soon enough that we haven't finished this goal, but the goal of this project is that we be able to take choreography and automate everything from the choreography to the motion commands that drive an autonomous robotic marionette system. So these are the various marionettes that we've built so far. These are actually 3 of the 5 systems that we've built. This is one of the earlier ones. So this is a little vehicle that runs on the underside of a tarp, dragging this poor ferry along. And you can tell that it's not all that exciting. It's pretty sluggish. This is a robotic butterfly that the same student made out at Disney by the end of the summer. And that's actually, considerably better. Let me play this again. This is almost the most recent one. So these are epochs that have magnetic wheels on the bottom of a steel table. And the nice thing is that you can really see. So he's supposed to go over there and then wave his arm. And as soon as you try and make him wave his arm, the whole puppet starts rotating back and forth. I mean, the dynamics for these systems really matter. There's no inverse kinematics that are going to fix these problems. So whatever we do to try and control the puppets has to include the dynamics in a real way. But nevertheless, the specification that we want to use is this very high-level specification. We don't want to have to worry about the dynamics. We just want to be able to make it do interesting stuff. Now, the problem with the epochs is that it turns out that they can't carry much of a load. The motors burned out in no time. They were super expensive. So now the new version of this is something that we're building ourselves. Disney was tremendously helpful in helping us with the design for this. And they can now carry 25 pounds each. They can zip around on the bottom side of a tarp like this one, and generally they're localized pretty well. So the actuation, we're finally to the point where we think we can do it reasonably well. And what we're trying to do is, we're calling it the Pygmalion Project. So Pygmalion was the sculptor who fell in love with his own creation. As roboticists, I think we can all relate. And we had these dancers come down to Georgia Tech and get in motion capture suits. I had a theater student write us choreography that used as limited a number of motions as possible so that we would hopefully have something that was tractable for actually implementing a robotic marionette play. And then we did motion capture. And so you should be thinking of these as the reference trajectory. So this data here from these actors is the reference trajectory that we want the marionettes to track. And so we have a representation of that data directly in the generalized coordinates of the marionettes. And so the question is, if you want to create a piece of choreography, like one of the words in your set of choreographic specification, then how do you make that happen with some sort of a feedback law that uses this as the reference? So some things to note. It's worth commenting that the marionettes are real physical objects, right? This isn't the same as animation tasks, where if you can get it to look right once, you save it to a file and you're sort of done. It doesn't matter if it was unstable or there's no questions about uncertainty. There's a lot of things that aren't present in the animation setting that are present in this setting. So any motions that we come up with, they have to be repeatable. And so for us, that means that they have to be stable. That the reference trajectory and the controller that we're using to control that reference trajectory has to be a stabilizing controller. And piecing choreography together should not destabilize the physical marionette. And the only reason that it's important to note that that's a relevant thing is that oftentimes it's unintuitive that switching between stable motions can destabilize a system. But in fact, you can sort of imagine if I told you to run and then a little bit later I told you, walk. That would be easy for you to go ahead and track. But if I kept on going back and forth right in mid-gait, run, walk, run, walk, run, walk, that would, of course, be very confusing, right? I mean, if you really tried to do it instantaneously, you would probably trip because the gaits for running and the gaits for walking are actually quite a bit different from each other. And so piecing the choreography together should somehow insist on a stability criterion in terms of how you piece them together. Okay, so then the last thing is I just want to talk a little bit about if we're trying to design controllers for high-dimensional systems like this, high-dimensional systems like the marionette, high-dimensional systems like the hand, what sort of architectures do we have at our disposal? And a lot of software for high-dimensional systems, right now it really focuses on just the simulation piece. So Open Dynamics Engine, which a lot of people use, is one possible choice. DVC, which is the code that Jeff Trinkle and his group developed, which is good for contact mechanics. It solves for contact mechanics using LCPs. And like Oops and P is the code that Lydia Kravaki down at Rice has developed for testing planning algorithms. But these are largely not control-oriented. The main sort of approach is model predictive control, the most standard version of which involves discretizing your system in time, maybe using something like the Open Dynamics engine as an input, and then discretizing in time and trying to solve some huge dimensional optimization problem and see what it gives you. We find that unsatisfying for a number of reasons, not the least of which that there's no notion of stability for that optimization approach. The most similar thing is NTG. So a lot of people have heard about this software. This is some trajectory optimization software that was developed at Caltech. The only reason I know about it is because I was there when it was being developed. But it actually uses the differential structure of flight mechanics and other sort of comparatively low-dimensional problems to develop aggressive maneuvering. And the key thing about it is that because it has this extra differential structure, they can run it in real time. So this is one of the few examples of software-enabled real-time optimal control that can actually robustly stabilize something that's very, very unstable. And so the questions then are, well, if we're going to develop software for the marionettes, what does that software need to provide? And so what I'm going to do is I'm going to spend the next just couple minutes talking about a very simple example. Sort of, and if I told an undergraduate about an optimal control problem or just a control problem that I wanted them to solve, it might look something like this. So this is a cart pendulum problem. You get to push on the cart, and then the pendulum is free. And you want to invert that pendulum. And so the dark blue circle right here is what the real pendulum is able to do. And the light blue circle behind it is the reference trajectory that we'd like it to track. And one key thing to note is that that reference trajectory is not dynamically feasible. So it's not something that the real pendulum can do. But it's enough information about what you want it to do that it can do it stably. And so this is something that you can invert it, and then it comes back down. And so you get that little bit of a swing up motion, which is sort of, I mean, that's sort of what we expect. If I actually handed this to someone, they would probably oscillate it a little bit before they'd try and flip it up. So one of the first things that you do in modeling a system like this is you choose coordinates. And this is often something that we sort of overlook as a fundamental part of the modeling process, which is a little bit funny because choosing coordinates is often the last time in the process that you have really any choices about what you're going to do. In the coordinate choice here, this is a rigid body and this is a rigid body. So in principle, we could say, well, we're going to give each one of those rigid bodies an element of SE3. So we have 6 dimensions, 6 degrees of freedom for each one. And then we're going to apply a bunch of constraints to it. And so that means, our state space is 24 dimensions. We've already increased the dimensionality of the problem that we're trying to solve by a lot. Whereas if we just say that, well, 1 degree of freedom is the x location of the cart, and the other degree of freedom is the angle of the pendulum, we've reduced that down to 4, which starts to feel a lot more manageable. Automatically choosing coordinates is not all that easy to do, although Hatton and Choset in the most recent ICRA talked about this some, like how to choose coordinates in a nice way or for modeling purposes. And also, people in Numerical who do numerical integration of PDEs do this all the time. Like when you choose basis functions, that's what you're doing, is you're choosing the coordinates for this infinite dimensional system that you think are most important. But for us, for this problem, one of the key things is that the coordinate choice has a huge role to play in whether or not you're talking about a controllable problem. So that 24-dimensional representation, all those constraints mean that it's not controllable, which means that if you try and solve for an optimal controller, it'll almost certainly be degenerate, which means it's not going to be numerically stable to solve for. Whereas if you have a lower dimensional representation, the likelihood that you're going to have a numerically well-posed control calculation is much higher. So in everything that I'm going to talk about, I'm going to insist on the ability to specify problems in generalized coordinates. So we're not going to allow ourselves to only work in Newton-Euler coordinates. Okay, so if we're doing this, the next thing that we would do after choosing coordinates is we're going to write down the dynamics. And if we can write down x dot equals f of xu, so u's are the inputs, x is the state, X is typically the configuration and the velocity of the configuration. Then we can do a sample-based approach, like something along the lines of find a clever way of sampling U such that we have probabilistic guarantees about whether or not we can track the trajectory that we want to track. And that can lead, it can be computationally expensive, potentially, and it can lead to irregular looking trajectories because of the sampling process. More than anything, I'm concerned about the fact that we need trajectories that are insensitive to uncertainty, and so therefore I want there to be a feedback law in what we're doing. And so the sample-based approach is something that, from the outset, I'm sort of just dispositionally likely to avoid. So if we were going to do that, that means that we have to be able to compute the linearization. So A of t is some matrix that tells us how the derivative with respect to the state changes as a function of the state. And these two notations mean the same thing. This is called the slot derivative. B of t tells us how f changes with variations in the control. And so solving this equation subject to some quadratic cost function requires the solution of a Riccati equation. And so what you should be taking home from this is that if we think about the fundamental equations of control, there's more than simulation involved. There's the nonlinear simulation, just like there is in probabilistic planning. But there's also computing the linearization given this data. And then there's the computing the Riccati equation that gives us the stabilizing controller. And so we're viewing all three of these pieces as being sort of fundamental pieces that software has to provide to us in order to solve the control problems that we're trying to solve. And we have to do it without being able to write down f. Because of course with the skid-steered vehicle, it's just simple enough that you can write down an explicit model. And that means that you can take the derivative explicitly and write down what A of t would look like and write down what B of t would look like. And that means that you can write down what this looks like. But in general, for something like the marionette, there is no possibility that we're going to be able to write this down explicitly. And so we need to figure out a way to do it solely in the software. And that's something that control theory has historically not done a great job at. In fact, probably in this crowd, I won't insult anyone if I suggest that one of the big difficulties with control theory historically has been that the examples that we use are always really, really trivial, but the applications that we care about are typically pretty complicated. The only real exception to that is when you happen to have a linear time invariant system that you care about, like a power grid system or something like that, where suddenly MATLAB provides the abstraction because you can write down things in terms of matrices. And that's really helpful because it allows you to test your ideas on a low-dimensional problem that you can think about, that you can think about a two-element circuit and solve a problem in that setting. And then, after you've really thought about whatever it is you care about coherently there, then you can move to the 1,000 degree of freedom system that is represented by your electric grid or whatever. So that's the type of thing that we want. We want to be able to use the same abstraction to compute controllers for the marionette as we use for the cart pendulum problem. Okay, so in terms of what we might want from software, we'd want the linearizations. If we want to be able to guarantee quadratic convergence, which it's known that that's necessary for real-time operation, like you can prove that it's necessary for real-time operation, then, or that it's sufficient, actually, for real-time operation, then our choices are we can write out the dynamics and differentiate them by hand. For anything complicated, that's not going to be doable. Alternatively, we could automatically differentiate it using some sort of software, Mathematica or Maple or something like that. And that actually turns out to be pretty slow. Like just doing algebraic replacement rules turns out to be pretty slow. If we did this, when we did this for the marionette, it took Mathematica a week, I think, to linearize the system. And that's probably not going to be the most useful thing. And then even when we saved that file, right, I mean, it was this enormous file. It was just completely unmanageable. So that means that we need to think more carefully about what we're going to do. Now, let's say that you can compute these things. What else does it buy you? Well, the primary thing that it buys you is that if the Riccati solution exists, then that actually gives you a guarantee about stability of the controller that you're obtaining. And so that means that computing this Riccati equation isn't just, well, I need some sort of feedback gain. It also actually tells you something important about whether the system can be controlled, which is awfully helpful. Like it's helpful to know that when you're doing these computations, the software can actually tell you something about the structure of the system that you're trying to work with. So the convexity of solutions is often nearly global. Like these feedback controllers, because there's feedback involved, there's some robustness built in, and they typically have a very large basin of attraction. But it's not going to be global. And probably at the very, very end, I'll talk a little bit about what one might want to do about that. Okay, so if we use this technique, this is a simple system. So this is just an arm that's trying to imitate someone waving. So they lift their arm, they wave at you, and they lower their arm. Let me play that again. And the key thing is that this calculation, when we did it in Mathematica, it took a few minutes. It took like 3 minutes, 4 minutes to run. But then when we implemented it on the experiment, it worked first time. So this is very slow, right? I mean, clearly we don't want to actually be computing anything in Mathematica. But as a way of testing whether or not the results work, this gives us a reasonably good indication that we can stabilize the motion even though we're only pulling on things with strings.
Question.
Yeah?
On the left-hand side, is that a string and those strings push and pull, or is it pull only?
It's pull only. The puppeteers, when we talk to them, say that they never let a string go slack. And so we actually purposefully avoid controllers that pull so hard that the inertia of the arm makes the string go slack.
Okay.
And we're certainly not modeling the dynamics of the string. Right? We're assuming that the string is so light that, that it's acting as a constraint on the end of the arm. Now, the gray line is the desired trajectory. I should probably show that again. And so you can see that the arm itself tracks almost perfectly the desired trajectory, but the string doesn't. One other comment. So this converges in just a few iterations. Like you'll get a trajectory that looks almost as good as the one that I just showed you here in 2 iterations of the optimization. And this one is actually after 7 iterations. But I mean, it's definitely, we've overkilled on how much computation is needed to make this work. But the real question that we're facing is how do we do this calculation quickly? Okay, so that's how we can get pieces of choreography. Let's say that waving was one of the things that we know we want to do. Now, how do we take a bunch of motions like that and piece them together? Because that's a different question. And in particular, the way puppeteers do this is they describe the process in terms of imitate, simplify, and exaggerate. So they imitate a motion as well as they can. Then they simplify that motion down to sort of basic components, and then they exaggerate it so that the audience understands what's going on. We have a reasonably good idea of how to do the simplify stage. We have no idea how to do the exaggerate stage. But it shares traits with computer languages. I mean, they're very, very specific about how they write things down. So these numbers indicate beats. The puppeteers behind the stage actually sort of bob in rhythm with each other to make sure that they stay in sync. So there's somehow a synchronization that's critical to getting the puppets to interact when you can't see them very well. And then they have all these sort of motion primitives, right? It hops in place. It flies. Somewhere it says it flies. It turns and hops. It dances. And each one of these motion primitives corresponds to some sort of dynamic motion of this 40-degree of freedom object. And so that has to be interpreted and then not allowed. You can't let lean out and dance interact with each other in a dynamically bad way that makes the puppet become tangled or that makes the puppet start to become dynamically excited. So the way that we formalize this is we say that the dynamics are of the form x naught equals f sub I, where each f sub I corresponds to some piece of the choreography. And now the control that we have is when we transition between motions of the choreography. There's some nominal time that we'd like to transition, so I'm going to hop for a bit, and then I'm going to dance for a bit. And I'd like to roughly say when that transition is going to occur, but I'm going to choose when to do that transition. And you can sort of imagine if I'm walking, then I might want to choose transition between walking and running when I'm in a double stance mode, when I'm in the most stable position for suddenly accelerating, rather than doing it when I have sort of in free flight. Right, I mean, it's not clear. It's not clear that that's the right thing to do. But there are going to be better times and worse times to do these transitions. And in particular, so this is a walking and waving, or no, it's waving and then walking. This is, I don't know how many of you know Magnus, but this is the puppet that the Atlanta Center made for him, and it looks a lot like him. So the puppet waves, and everything's fine, but then when it starts to try and walk, transitioning at the nominal time, the whole puppet starts vibrating. And in fact, you can't even really tell that it was attempting to walk. So the motion specification somehow interfered with the interpretation of the walking motion at the end. So what we want to do is we want to optimize over these taus so that we get so that we avoid energetically exciting the marionettes. And that optimal control problem basically depends on the following two equations. This is the adjoint equation that tells you how to take the first derivative. So basically, rho is a rho vector. So it's of the same dimension as whatever your state is. And then you evaluate this, and that allows you to find the gradient. Now, the problem is that the gradient isn't enough to get fast convergence. So if you want to take the second derivative, it took us a long time to figure this out. So this, by the way, this first derivative, lots of people have already done this. It's been discovered over and over and over and over in a bunch of different contexts. This second derivative, as far as we can tell, no one has worked with it before. This is a Riccati variable. It's a matrix. So that thing is a square matrix where the m is the dimension of your state. So it's kind of a higher dimensional thing that we might want to work with. But if you can calculate this, then you can get a second derivative of the objective function. That is the energy of the system that you're trying to keep low. And it's worth noting that these two equations, this is the classical Riccati equation that we use from smooth control. And really, this equation and this equation are the same, except that there's no input term. And that doesn't seem like a coincidence, or it seems like a bit of a coincidence. The first time we figured this out, because we didn't know what we were heading for, the proof was like 5 pages long, and it was this horrendous mix of differential measures and all sorts of horrendous things. But once we knew what we were looking for, then we figured out a different proof that was, about a paragraph long. And so you can, when you know what you're looking for, you can often make things work out a lot more nicely. But the key thing here is that we can guarantee, if we can calculate this and this in software, then for this choreographic control, we can guarantee quadratic convergence, which means that we can guarantee that things will go fast. So this is the log of the gradient, and this is what that looks like versus iteration if you're doing a first-order method. And there's two problems with this. One is you're not getting very much improvement on the cost. Like the gradient is not going down all that much as you optimize it. The bigger problem is that you have no really good way of deciding when to stop. Right? Because, are you just going to choose some random 10 to the minus 5 as your cutoff point? I mean, maybe, but that's sort of arbitrary. Whereas here, with this quadratic convergence that we get from Newton's method, it's very easy to test if you're in that quadratic region, which means you're done. And so here, not only do we get fast convergence in just a couple of iterations, but we also know that we've completed the optimization. And when we do that, so here it waves, and then it walks, sort of. And so you can probably guess what the problem is here. We chose the objective function badly. We knew that we were somehow destabilizing the marionette, and so we chose to minimize the energy. And so now we've really missed out on this exaggerate phase, right? Because now this is the dullest motion imaginable. for the marionette, right? I mean, no one is going to, except for maybe in a talk like this, no one is ever going to want to watch this marionette. And even here, there's some question. So these techniques, we're still working on how do we generate meaningful objective functions that both preserve stability and allow us to exaggerate the motion to get large motions. But the techniques that we developed for the marionette actually do a really good job in some other settings. So for instance, let's say that you have some trajectory that you're trying to track, but the only thing that you get to measure in the world are landmarks in the environment. And those landmarks are things that you get to go towards. So they're like reflectors. And so you get to shine your light, and you know which reflectors are which, and you get to run towards them. But that's it. That's all you get to do. It turns out that going towards each one of these things is a different mode, right? It's a different piece of the choreography that the robot can follow. And if you think about there being two trees, E and F, and as you pass up this way, down here, E from the point of view of the red dot looks like it's on the left. But when you go up here, suddenly E from the point of view of the red dot is on the right of F. So the order of E and F have changed as you've moved across this line. And let's say that that's the only information that you're allowed to use in order to robustly track this. So it turns out that doing a hybrid optimal control version of LQG techniques, linear quadratic Gaussian techniques, it solves this problem really nicely. So the yellow dot is the open loop dot. That's what happens when you stochastically force the system without taking into account any of the measurements. The black dot is the actual state of the system, and the brown dot is the estimate. And you'll notice that whenever the brown dot gets off a little bit, so it does right here, then suddenly it jumps back right when it crosses that line. And so what's nice about that is that we really know this black dot is able to follow this desired path only using very, very, very limited information in the world. So the original design was based on continuous sensing, but we were able to rephrase that design purely in terms of landmarks in the environment. And so you can imagine doing this in a manufacturing setting where you want a robot to follow the same path over and over and over, but you don't want to use indoor GPS. Another example where this technique, the hybrid optimization techniques, works really well is if we're tracking this vehicle and we want to know when it transitioned between stick and slip, then this is recording at 1 hertz. It's pretty crappy GPS data. It's coarse. And we have a model. And using the model, we can actually, directly from the data and from the interpolation of the data, figure out estimates of when the transitions occurred and what those transitions were. So both questions. Here it'll estimate that we were in a stick state, and then around here it estimates that it started turning, and then it estimates that it went back into a stick state. And that converges quadratically in just a few iterations, and even more importantly, with that quadratic convergence, you gain a lot of insensitivity to noise. So we know that the noisy situation is something that we need to be concerned about. We certainly can't expect deterministic equations when we're doing these optimization procedures. And first order methods, I mean, not that one would generally use first order methods here, but first order methods bottom out because the line search can't overcome the noise in the system. There's just not enough structural information in the optimization. Okay, so those are the computations that we want to be able to do. We want to be able to do the smooth optimal control so that we can generate motions. We want to be able to do the hybrid optimal control so that we can transition between those motions. And we want all of that to be encoded into the software that we're using. So what do we need to do that? What is the software architecture requirement for simulating and controlling something like a marionette or something like a hand? And for a long time, we thought that the answer to that would be that differential algebraic equations would be the right way to go, because that's what people have used for 2 decades. They've used them in lots of applications. And when we use them, this is what happens. So there's just something wrong. And the reason that that happens is because we started out with no dissipation in the hand. Because we thought, well, we want to be able to find that as a system identification problem. We don't want to have to guess what the dissipation is ahead of time, because the physiologists that we work with tell us that it's really, really hard to figure out, based on physical data, what the dissipation should be, whereas the other mechanical properties are things that we can know pretty reliably. Moreover, with the marionettes, we found that if we used DAE techniques, so there's no impacts here. That's why the bodies can pass through each other. Then everything looks fine for a little bit, but eventually we start to run into some pretty serious problems. So there's no forcing. This puppet's just swinging back and forth in gravity. And yet, if I used this trajectory to design a controller, the controller is going to be trying to undo all of the effect of the simulation. And so it's not going to be physically realizable. It will destabilize the real physical system if you try to apply it. And so the reason that these didn't work is because we were unwilling to do the standard thing that people do using differential algebraic techniques, which is they stabilize the constraints. And because we wanted it to be repeatable, we were unwilling to stabilize the constraints because it changed the physics of the problem too much. And now we're using variational integrators. These are a type of mechanical integration that uses the action principle as the starting point instead of using the ordinary differential equation as the starting point. I'm not going to get into the details of this. The key idea is that what we basically did is we used Featherstone's sort of philosophy of how to do simulation of robotic systems, but we did it in the context of variational integrators. So the idea is, and this is a very, very standard way of organizing data about a system in computer science and in animation in particular, but it's not at all standard in control theory. So it took us a while to figure out what the right thing to do was. Vertices correspond to the individual bodies, and so any external forces acting on that individual body is associated with the vertex, and inertia tensors are associated with the vertex. And then edges describe the geometry between two vertices. So if I have one center of mass here and one center of mass here, then there's some rigid body transformation connecting those two center of masses that depends on the elbow angle, right? And so the entire system gets specified that way. And from that system, we want to calculate the discrete Euler-Lagrange equations, which come from the variational integrator. And the nice thing about the discrete Euler-Lagrange equations is that because they come directly from Lagrange de Lambert, the constraint is incorporated directly into the mechanics. It's not incorporated separately. And so this is a root-solving problem. If you know qk minus 1 and qk, so roughly speaking, you know q and its velocity, then you can solve for qk plus 1, subject to the constraint that the new configuration satisfies the constraint. So what's nice about this is that it allows you to simulate systems with closed kinematic chains without any sort of tuning or constraint stabilization. And so what we're really doing is we're just constructing this big graph, and the graph has closed cycles in it. And once we've constructed the graph, then that should be the end of what the user does in terms of generating a model. Everything else, all of the dynamic simulation, all the linearization, the Riccati equations, all of that should be done automatically. And so when we do that, the simulation actually works, I think, pretty well. I mean, this is a marionette being simulated at 5 different time steps. The biggest time step is 1/10 of a second, which is getting pretty close to the same time scale as oscillations of the marionette. So you're only getting a few samples per oscillation of some of the rigid bodies. And it doesn't diverge very much. I mean, the one that is diverging the most is the one with the biggest time step, but we aren't seeing any sort of physically implausible behavior. The computation time per iteration does not change a whole lot. And so a 1/10 of a second time step is roughly 10 times faster than a 100th of a second time step, even though there's a root-solving procedure involved. And this is, by the way, so just the simulation stuff is available at trep.sourceforge.net. Trep stands for tree representation. Now, more importantly, another thing to just be aware of, variational methods are actually quite good at representing impacts. And so this is a simplification of the Rex robot out at Penn, and I think there's one here as well. And So one of the reasons that we were originally interested in these things is because they allowed us to deal with impacts in a nice way. Okay, so if we want to do linearization based on the graph, there are two challenges. One is the complexity of the mechanical system. The other one is the fact that we aren't actually working in continuous time. All of those equations I wrote down, x dot equals f of xu, z dot equals a of t times z plus b of t times u, none of that is what we're actually going to be computing. And so the difficulty there is that if we linearize that continuous representation, we're going to get some a of t, and then if we want to know what the linearization looks like over the discrete time step, we're going to end up basically doing a matrix exponential. And the difficulty there is that that matrix exponential won't satisfy the constraints. And so your linearization will not respect the constraints on the system. And so that means that the control law that you're going to calculate will always be fighting the constraints in a way that's sort of not real. And so what my student, this is Elliot Johnson's work, and what's exciting about what he figured out is that we were just looking at the wrong problem. That if you simply change from looking at how the continuous dynamics change with respect to continuous perturbations in the trajectory to how the discrete dynamics change with respect to variations in the discrete trajectory, suddenly you get an exact representation of the linearization. Now, proving this is a nightmare. It's literally 30 pages of algebra showing that everything works. But what you should take home from this is that you can actually derive a formula based on the graph that gives you an exact representation of the linearization, even for closed kinematic chains, even for contact problems. You get an exact representation. And it's purely algebraic. There's no root solving. There's no matrix exponentials. It's just easy. And so when we're simulating the marionettes, we can calculate the linearization as quickly as we can calculate the simulation. So that means that we can just be calculating them both together. Anytime you want to know, is my system locally linearly controllable? Like, is it allowable for me to compute a local stabilizing controller? You can just check. And that data is available. If you want to compute these Riccati equations, you can just do that as well. In the case of closed kinematic chains, you get a linearization that has an eigenvalue of exactly 1, because that eigenvalue corresponds to the fact that the closed kinematic chain can't separate. And so it's 1 all the way to machine precision. So this starts to mean that we have numerical methods that can be used for these comparatively complex systems, but that have the numerical properties that we might want. And so now, so you already saw both of these optimizations. Both of these optimizations take a couple seconds to run in our software as we currently have it. And a more important point is that they run in the same amount of time. So this is a 2-degree of freedom system, and this is a 4-degree of freedom system. But the amount of time to run the two optimizations is the same. And so the question is, and this involves a closed kinematic chain, because the shoulder is inertially fixed, and this endpoint is moving with respect to that same frame. So how can this, which has a state that's twice as big, take the same amount of time to optimize as this? And the reason is because we're doing feedback control instead of doing some other optimization technique. When you do feedback control, you're generating a feedback controller, which means you're getting some robustness. And when you do the line search in the optimization, you get to take a larger step, so it takes fewer iterations to optimize. And this system is simply easier to optimize. It's easier to control than this system. Like, the reason that everyone uses the cart pendulum is because for a 2-degree of freedom system, it's one of the hardest nonlinear control problems that you can come up with. Whereas this is actually not so hard. And so what we think is going to happen, but we don't know it yet, is that the puppets, even though they're very, very complex, we think that what's going to happen is that structurally, they're actually pretty easy to control. The puppeteers tell us this all the time, that they design puppets to be easy to control. And so what we want to see is we want to see that sort of ease of design to be a natural outgrowth of the Riccati equation, of calculating the Riccati equation. Okay, so I don't have a marionette play to show you, because we actually haven't been able to do these calculations yet for anything but the arm. The linearization is what we needed, and my student only finished that in the last month. I'm hoping that maybe in the next month or so we're going to have some exciting things up on YouTube. But what I can show you is going back to the hand. So when you simulate, the hand turns out to be easier. It's easier than the marionettes for a variety of reasons. And so the variational integration of closing the hand works fine. There's no dissipation in this model. We're using this with colleagues at the Rehabilitation Institute. And we decided, okay, well, we should be able to grab a ball and stabilize it to the palm. So we're just doing linear quadratic control here. And what everyone told us who works with hands is that the right solution to that problem is that the hand should just relax, right? Because it's passively able to stabilize the ball. And that's actually exactly what happens when we compute the optimal controller, is that instead of rigidly lowering the ball, the tendons just relax and the ball settles. And so somehow the optimal controller is actually capturing the way in which the compliance of the physical system facilitates the manipulation task. Okay, so the key points that I want you to take away from this. One is, we think we have a pretty good understanding of how to specify choreography as a control problem to solve in terms of these hybrid control procedures and hybrid optimization, and how to generate motion primitives for the marionettes based on sort of more classical methods in optimal control. Moreover, we're becoming increasingly convinced that the software architecture is doable. That just because right now the software that we all use, like when we download Open Dynamics Engine and use that, just because it doesn't provide linearization information doesn't mean that we can't get it by writing our own code and spending years. But the linearization information is helpful enough that it means that we should be asking for it. The hybrid control stuff that we've been using is not yet working as well as we'd like it to for the marionettes, but it works really well for other example systems. And we've also used it in some air traffic control problems where it really just solves this global optimization problem very, very efficiently and nicely. And that one of the key things is that for scalability, there's two things that you might want to be concerned about. The classical CS thing, which is worrying about linear scaling in the number of rigid bodies in the system in terms of computing the dynamics. But the other one is this second order optimization, like making sure that you're really guaranteeing quadratic convergence, because that makes things converge so much faster that you lose a lot of the dependence on the dimensionality of the problem. So the next thing that we're working on, this is actually work with Jerry Marsden at Caltech and Melvin Leoch out at UCSD, is figuring out how to take this and based on the topology parallelize all the calculations so that we can get what is probably the low-hanging fruit of distributing it across multiple processors. We'd really like to know what the relationship is to topology-based planning, because like I said before, the controllers that we get are often near global, but they aren't actually global. And we'd like to know like what else is required, like what additional mathematical structure is required in order to get a globally complete picture of how to solve these planning problems. And we've already seen some evidence that we can numerically design puppets to be easier to control, and that's actually a useful thing to do, that it makes all these calculations easier. And so sort of posing the control problem as a simultaneous design and control problem is, I think, a more reasonable way of dealing with these high-dimensional systems. So Magnus has been great in all of this. Our collaboration has been tremendous. The Atlanta Center, primarily just talking with the puppeteers, is amazing. Lanny Smoot at Disney is an amazing design engineer. My graduate students, my engineering graduate students, Elliot Johnson, Tim Caldwell, and Jarvis Schultz have been tremendous, and Elizabeth Yakum is my theater graduate student that's been helping us write the choreography. If you have any questions, I believe all these papers are on my website. Both of these are on hybrid control. This is on the variational integration, and this is a two-page overview in Puppetry International started by Jim Henson. So which is kind of cool. And this was actually the original paper that Magnus and I wrote about puppet choreography. Okay, and with that, and even more or less on time, are there any questions?
So I wanted to ask about that global versus not totally global
right.
stability. Can you characterize the region of stability where these controls
So the standard way of characterizing regions of stability is implementation of sum of squares techniques, where you actually construct the Lyapunov function that corresponds to the stabilized region. That is what I want to do in our software after we've successfully stabilized the marionettes at all, right? And like even without uncertainty considerations and things like that, I want to do sum of squares type techniques to estimate those basins of attraction. The problem is that sum of squares techniques work really well if you're working with a low dimensional system where the state is relatively low dimensional. For such a high dimensional system, I'm a little bit concerned that bad conditioning of the optimization problems that you have to do might lead to multi-scale optimizations where you actually don't have enough machine precision to do the calculation that you need to do. And I mean, people who use sum of squares techniques for PDEs run into this all the time. And so I'd rather avoid some nightmare of a multi-scale problem for now if I can. Other questions?
So you mentioned a couple things. You mentioned that you don't let the strings go slack.
Right.
And you mentioned that one of the things you want the controller to do is not to cause the marionette to swing in between motions, right? So both of those things sound like damping out unwanted dynamics.
Great.
So do puppeteers do actions that actually excite dynamics and use those, or do they mostly try to keep that stuff from happening at all?
They do both, which is part of what makes designing an objective function that will facilitate the motions difficult. So what they do is they sort of conceptualize the drama of a motion in terms of particular moments that they want a big motion. So like if they were imitating, they would say that my imitation of a waving motion is too precise. Like that if I had, that what they want is to take motion capture of someone going like this and turn it into this, right? Like big motion, but then at the end of that motion, damp it out prior to the next motion. And so there's something about the objective function in a way needs to be a time-varying objective function that varies with the choreography. And we know that, but we want to get to where we can actually do the calculations that we want to do for the full marionette before we start worrying about what might end up being just a detail. We just aren't sure yet if it is or not.
So 2 questions. So the first one is a follow-on to what George said. So I would imagine if there's one behavior like dancing, another behavior like waving, that the marionette people do, that the transition from one to the other may require either a blending of the 2 behaviors that would be different from dancing to, say, pointing with your foot.
Right.
And what I heard from George's question was, no, there isn't a special transition. All we have to do is worry about damping out transient dynamics. So
my feeling on this is that it depends on the type of motions that you're transitioning in between. So if the 2 motions are sort of nicely compatible, right? If one motion nicely feeds into the other motion, then just sort of smoothly transitioning from one to the next might be the right thing to do.
Right.
And in particular, so imagine that I want to wave and then I want to lean, right? If the choreography specifies that I should lean when my arm is over here, I will certainly want to wait until my arm is just already kind of over here, and then I can just lean down. But that's a very different problem from if I'm going to do something radically different, right? Like if I'm just sitting here, or if I'm walking forward, and then I'm going to jump, there might be a lot of damping right before the jump. And so how to sort of design those motions to facilitate transitions? We know that there's probably some sort of grammar in terms of what motions are allowed to be concatenated. But we don't yet have any of the computational infrastructure to even ask that question. But it's a clear thing that we need to address. Like, how do we know what motions can be connected to each other?
Right. We actually, Magnus, Jordan, and I have actually been talking about that.
Yeah.
With other things. The second question is, with the coordinate optimization, so I got a little lost. I got lost a lot. Was the point that you came up with a systematic way of choosing optimal coordinate systems, or was your point that there's an opportunity to use your intuition?
It's absolutely your opportunity to use your intuition. Like, our feeling has been that our brain is really good at assimilating what degrees of freedom are the important degrees of freedom. And in particular, like the puppeteers talk about the elbow angle all the time. But in the actual puppet, there's no physical mechanism there. Right? It's just cloth. There's a hand, and there's a shoulder, and there's cloth connecting it. But they abstract that, potentially infinite dimensional thing as a single degree of freedom. And given that that's true, we said, okay, our brains are in the loop when we're choosing coordinates. Yeah, absolutely.
Okay. All right, thank you. I'll follow up with that. Any more questions for our esteemed speaker? Okay, well, let's thank him again. He came a long way to this stuff.